Hey guys, this is Professor Janacek, and I want to talk to you about surface integrals. Let's begin by looking at surface integrals of scalar-valued functions. For a surface S given by z is equal to g of xy, so z is defined by g, we have that the surface integral of f of xyz with respect to s is the double integral of xy g of xy times the square root of the partial of g with respect to x squared plus the partial of f with respect to y squared plus 1. And again, we're integrating with respect to area here. Now, this might start to look kind of familiar. It has a similarity to finding arc length, and we'll see a connection here. Now, if our surface is given by a parameterization, which we'll call R, and notice R has the parameters u and v, so we actually have two parameters here. Our surface area, our surface integral, becomes the double integral of f. Notice all of those components of f, x, y, and z, are all defined by our parameters u and v, times the magnitude of the cross product of t sub u and t sub v, where these are unit tangent vectors in the directions of u and v. So we've got t sub u is dr du, and t sub v is dr dv. So what does this mean? Well, the easiest way to understand a surface integral is to recognize that we have this connection. Thinking back again to arc length, you could say that arc length is to a surface area as a line integral is to a surface integral. So arc length, line integrals, those are both along a single curve, whereas a surface area, these surface integrals, those are kind of two parameter things. So it helps to know that this is a one parameter situation, whereas our surface area and surface integral, we're looking now at two parameters. So understanding this idea of a surface integral versus surface area, notice that if f of xyz is equal to 1, then the surface integral actually equals the surface area of our region S, of that surface S. All right, so let's take a look at an example. Let us evaluate the surface integral, double integral of f of xyz with respect to our surface for f of xyz equal to y, with our surface being defined by the cylinder x squared plus y squared is equal to 9, with z, our z value going from 0 to 3, and we want to use a parametric description of this. So to begin with, let's take a look at our surface. X squared plus y squared is equal to 9, but we can write that as 3 squared to help us with the parametric description. So parametrically, this could be written as r is equal to 3 cosine u sine u, and then our last component is just v. Some things to point out about this is that u goes from 0 to 2 pi, can go from 0 to 2 pi, and v will go from 0 to, let's see, it'll go from 0 to 3, and that's based off of this. Another thing I want to make note of, now I'm not going to go through the computation for this, but the magnitude of TU crossed with TV, that's this bit right here, that in this situation is equal to simply 3. All right, so now let's go ahead and set up this double integral. We're looking at the double integral over our surface of f of xyz ds. Now remember, f is equal to just y. So this is the integral, the surface integral of y ds. And we're going to simply use this here to evaluate that surface integral. So we're going to rewrite it as that double integral over the region R. All right, let's see. So looking at our regions, our u value, we're looking at the entire cylinder, so all the way around from 0 to 2 pi. And then it goes, the height of it goes from 0 to 3. And we're integrating just y. The y value here is 3 sine of u. Again, remember x, y, and z are all functions of u and v. And then again, following this, remember we have to include the magnitude of that cross product. So that's 3. And I went ahead and I've written these integrals. I've got the inside integral is v and the outside integral is u. So that means we will integrate with respect to v first and then with respect to u. Now, of course, it's absolutely possible to do that in a different order if it makes life easier, but I think this will work out just fine. So what we have here is 9 times the integral from 0 to 2 pi and the integral of from 0 to 3 of sine of u dv du. Well, integrating with respect to v first gives us 9 times the integral from 0 to 2 pi of v sine of u, evaluated from 0 to 3. We're still going to integrate now with respect to u. Keep that differential out there, don't lose it. So let's see, what does that give us? This computation isn't too bad. Ooh, that's not what I wanted to do. This computation really isn't too bad. That gives us what, just 3 sine u. So we have 9 times the integral from 0 to 2 pi of 3 sine u. It's 3 sine u minus 0 sine u, but that gives us just 3 sine u du. So all in all, that's what, 27 times the integral of from 0 to 2 pi of sine of u du. Well, that's an easy one to work. That is simply 27 times negative cosine of u, evaluated from 0 to 2 pi, which would give us 27 times, let's see, cosine of 2 pi is 1, So that's -1 minus cosine of 0, also 1, so that's another -1. Watch all those negatives in there. But there in the back we have -1 plus 1, which is 0, so all of this becomes 0. So there we go. This surface integral is simply 0. Enjoy!